this is my Mars autonomous landing AI. That's what I decided to name it. By me. So the project overview. So our goal is to safely identify optimal landing zones on Mars images, preferably top down. And some key features was patch-based terrain classification, risk scoring, which we'll look at, and like deciding out of which of these patches is going to be the safest. So as you can see, this would be like an image that gets put into the AI, and this would be the output. And like you can see like these flat, like safe looking areas right here, get like much safer like looking colors, but I'll explain those later. So this is the data set that we use. So we gave the AI to train with like a ton of Mars surface images, and they were organized by terrain classes. So these are the terrain, these are just some of the terrain classes here. So like a bright dune, a dark dune, craters, impact effecta, slope streaks, spiders, Swiss cheese, and we trained it with those. And like in all of these categories, like totaling, there's six or 7,000 like or more images. So the model architecture. So at first, the I was using the model, I was using a CNN model, but the results I was getting with the CNN model weren't very good. So I switched it to a pre-trained model, which is ResNet 18 transfer learning. And the way the model works, so you input the image, it trains it on 64 by 64 image patches, and the output is the hazard levels of each patch. And why I switched to ResNet, it was much more fast, it was like much more accurate, and it's just as easy to implement as the CNN model. So it was just like a very nice like model. It was a very nice path to go. So I had to upload my model to the public Streamlit app. So first I put all my essential files of the project into a GitHub repo. So as you can see, this is the app that the the main Streamlit uses, right? This is the main part. So this file main.py is what's used to actually train the AI. Um, readme.txt is kind of like an overview of like the whole AI. Like if anyone else wants to look at my GitHub repo, look at the project, what's like anything else. Requirements.txt, that's a page of the Python imports that are necessary to run app.py. So that's also necessary for running it on Streamlit. And runtime text, uh sorry, I forgot what that did, but if I look, I can show you later. And like, oh, I think it had something to do with a Python version, but I'll have to recheck. So you'll notice that in my GitHub repo, like my actual model isn't there. That's because it was too big to be put into GitHub's repo. So the model ended up being around like 43, 44 gigabytes, while GitHub only accepts files of 25. Oh, sorry, did I say gigabytes? I meant megabytes if I said gigabytes. But uh, the GitHub only accepts files of 25 megabytes or less. So I used another repository specifically for AI models called Hugging Face, and I can show you that too. But I put my model that I hosted my model through Hugging Face, and then I altered my app so it would import Hugging Face's model, like Hugging Face's import code, and call the model, like my model, on the Hugging Face repository. And then Finally, I linked my Streamlit to my GitHub account and easily deployed the project. But easily, I definitely had some troubles. But once you have all of this set up, it's very straightforward. So hazard mapping. Um, So the process is we divide the image into patches, we classify each patch, we just we assign a risk score 0 through 1, and then we generate a heat map. So you can see like I would say from blue to red is the heat map. So the blue areas are like considered the safer spots. Green is like less safe but still safe. Orange is like more hazardous, and red is hazardous. So as you can see, it classifies like these patches, right? So like the super bumpy terrain in the orange right here, that's considered like pretty hazardous. This big crater over here, this very bumpy terrain, that's considered extremely hazardous. And this blue terrain right here, like this, like if you look behind that obviously blue shade, you can tell it's pretty flat and doesn't have much really like imperfections. Like it looks pretty safe to the human eye. So it marks those at the safe spots and it chooses the most optimal one. So the Streamlit interface. So the way it works, as you can see, so first we browse your files right here at the top. You'll wait, sorry, 1 second. Sorry.
No worries.
Um, so you browse the files at the very top and you can select any file, like any image of Mars's surface. And it's important, there's an important reminder right here that only top-down Mars images work properly because the model was entirely trained off of top-down images. So like a side image, it might tell you to land like in the sky, right? And obviously like you can't land in the sky. So there's that. You can also adjust the patch size. So for example, this one has 32 patches, but you can adjust that from 16 to 64, I'm pretty sure. And once you input that, you can press initiate landing scan. It will give you this hazard overlay right here. It will assign a safety score where you want to land, like it's highlighted in the green right there, but it also gives you the coordinates of that landing spot. And it gives you a little legend here telling you like kind of what the hazard overlays mean.
Okay.
So my key takeaways from this project was that AI can detect the visual hazards quickly and pretty accurately. And a huge thing was switching from a CNN model to a ResNet model that made the performance much better. Like my accuracy jumped from like 75% to like 95% just from like the first training when switching to a pre-trained model. Um, the website is fully interactive and deployable. And one thing that I'll show later, but when launched to a public website, the model's capabilities are severely decreased, and I'll showcase that. So in the future, I would like to add more training images. You can never go wrong with a larger data set. It'll only make your project more accurate. Um, Improving terrain class granularity would be a good improvement as well. Using larger patches for speed would also be greater. Obviously, like using larger patches, making each patch smaller would increase the accuracy even more, make it more pinpoint. And using a proper server to avoid model limitation would definitely be one of the biggest things I would do. So this is the difference between a locally hosted, um, when you locally host the model versus when you deploy it to a public app. So this is the original image, and this is both using the same model and using the same like app and everything. So this is our original model. When it's locally hosted, you get so much detail from this. Like obviously, it's been shown in the other slides as well, how how like how much information it gave you with the risk score and where your landing was, such as that. And when deployed to this public app, it was Streamlit's like public free app with no like changes to the app or the model, you can see how much less detail this model has. Like it's very, very inaccurate, even though the locally hosted one with the same code has like so much more detail. So that's and then that's all there is in my slides, but I can showcase it as well. But yeah, those were my like that was my project. Any questions?